In this video, I want to show you how to analyze some bottle curve data in order to figure out the diameter of the bottle. So imagine you're filling a bottle by slowly pouring in uniform amounts of liquid, water, and measuring the height to which the water level rises each time you add the amount of water. So I show here in this table a little snippet of the data you might collect. So let's say midway through this process, you're adding 20 milliliter increments of water. So you go from 120 to 140. And at first the height level was 82 millimeters or 8.2 centimeters. And then after you add this 20 milliliters of water to get a total of 140, the water level rises to 87 millimeters or 8.7 centimeters. In other words, the water level rises by an amount equal to 0.5 centimeters. It turns out that there's information here that will let you figure out the diameter of the bottle. The picture is like this. When you add water to the bottle in uniform amounts, you effectively slice the bottle into slices that are cylindrical in cross-section, and the volume that you put in here makes the water level rise by some amount delta H. So each little bit of water gives you information about a thin slice of the bottle, and if the bottle is cylindrical in cross-section, you can figure out the diameter of the bottle from what's given. Here's how it goes. The first thing I want you to know, maybe you remember from chemistry class, is that a milliliter of fluid volume is the same as 1 cubic centimeter of geometrical volume. That's a given. So when you add 20 milliliters of water, you're figuring out the volume of that slice of the bottle. So the volume of the slice of the bottle is 20 milliliters, or 20 cubic centimeters. But you have a geometrical expression for finding the volume of a cylindrical shape. So the volume of a cylinder, you want to remember, is equal to the area of the base times the height. So area of the base times the height. That's the general formula for the volume of a cylinder. And in this case, since the cylinder has a cylindrical cross-section, its area is equal to pi r squared, where r is the radius of the base. Remember that the diameter of a cylinder is twice the radius, or the diameter of a circle is twice the radius of a circle. And then the height is this thing that I'm calling delta H. It's the change in fluid level when you add this 20 milliliters of fluid somewhere in the bottle. So this has to be equal to pi times r squared times delta H. Well, we have a numerical value for delta H. It's equal to 0.5. So you have an equation here that you can solve for r. I don't know if you want to solve things algebraically or if you would like to put in numbers, but here's how it would go. You have on the left-hand side the volume that you're adding, the volume of the sample that you're adding each time. Not either one of these volumes, but the difference between the two. On the right-hand side, you have pi times r squared times the height that the water level rises when you add this much volume. You have to solve this for r. Well, the way I would do it is like this. I would say that r squared is equal to the volume divided by pi times delta H. I'll just do things algebraically. I divide both sides by pi, which puts it in the denominator over here, and I divide both sides by delta H, which puts it in the denominator over here. And then, how do I undo the operation of squaring? Well, that's with the square root. So my formula is to take the square root of the volume that I added divided by pi times delta H. Let's see how it works in the case of this experiment. So the volume that I add is 20, pi is 3.14, and delta H for this little snippet of the experiment is 0.5 centimeters. You have to have cubic centimeters and centimeters here. So if you plug in 20 and pi and 0.5 and take the square root, I think you get 3.57 centimeters. That would be the radius of the bottle. The diameter of the bottle is twice the radius, and here I'd multiply this by 2 and then maybe round it off 1, because I don't think I have an experiment that's precise all the way out to the 100th of a centimeter. So if you double this and round it off, I get 7.1 centimeters as the diameter of the bottle at this slice. So that's a reasonable size bottle. Maybe it's kind of more like a cup. 2.54 centimeters an inch, so this is like 2.5 inches or so.